Picture this, you are cruising down an open road, the wind in your hair and the world at your feet. The journey is smooth, effortless, and you feel a sense of freedom that only driving can bring. But as you leave the serene landscape behind and approach the bustling city, the tranquility of the open road gives way to the reality of heavy traffic. Navigating through a sea of vehicles, each vying for space and position, driving become a delicate dance of speed and distance. In this complex environment, wouldn't it be remarkable if your car could think ahead, adjust, and ensure your journey remains as effortless as it started? In this video, we will explore the technology that promises to transform every drive into a seamless experience, no matter the road ahead. Welcome to our presentation on Adaptive Cruise Control, or ACC, a cutting-edge technology in automotive system that is transforming how we drive. We are Group 17, consisting of myself, Ammar, and Anwar. Today, we will be diving into the intersects of ACC, exploring its components, functionality, and the challenges it addresses. Our presentation is structured to provide a comprehensive overview of adaptive cruise control. We will start by comparing traditional cruise control with adaptive cruise control. Next, we will break down the key components and their functionalities. We will then move on the design aspect, including flowcharts and block diagram, and conclude by discussing the challenges and potential solutions associated with ACC. Let's take a journey back to the late 1950s, an era of innovation and the golden age of the automobile. In 1958, the automotive world was introduced to a groundbreaking feature in Chrysler Imperial. This wasn't just any car. It was the first production vehicle equipped with a technology that would forever change the long-distance driving, cruise control. And what's even more fascinating, this system was called autopilot. Imagine the allure and futuristic promise that the name held back then, a time when the idea of cars driving themselves was pure science fiction. Cruise control operates using simple yet ingenious mechanism. It employs a system of sensors and actuators that control the throttle, allowing the car to maintain a constant speed set by the driver. This means drivers could relax their foot on long journeys, reducing fatigue and making the drive more comfortable. This was just the beginning. As traffic conditions evolved and technology advanced, so did the need for more sophisticated systems. Enter Adaptive Cruise Control, or ACC, a technology designed to meet the demand of today's dynamic driving environments. As the automotive industry continued to evolve, so did the need for more advanced driving aids. Traditional cruise control, while revolutionary in its time, couldn't keep up with the complexity of modern traffic. Enter Adaptive Cruise Control, or ACC. Imagine a system that's not only maintain your speed but also adapt to the flow of traffic around you. ACC uses radar and camera technology to monitor the road ahead and adjust your car's speed in real time. ACC works by consistently scanning the road with radar sensors, detecting the speed and distance of the vehicle in front. When traffic slows down, ACC reduces your speed. When the road clears, it accelerates back to your present speed. A crucial aspect of ACC's functionality is its use of Doppler effect. So what is Doppler effect and how it works? The Doppler effect refers to the change in frequency of a wave in relation to an observed moving relative to the wave source. As an object moves toward you, the wave compresses, resulting in a higher frequency. On the contrary, as the object moves away, the wave stretches, causing a lower frequency. This phenomenon is commonly experienced with sound waves, such as the pitch of passing siren. Same principle applies to the radar wave used in automotive technology. In adaptive cruise control, radar waves are emitted toward the vehicle ahead. These waves reflect back to the car's sensors, and the change in frequency due to the relative motion between the two vehicles is analyzed. By analyzing the frequency change of the reflected radar wave, the AC system accurately determines the speed and distance of the vehicle ahead. This data is crucial for making real-time adjustments to your car speed. Using the Doppler effect, ACC can dynamically adjust the throttle and brakes to maintain a safe following distance. In this section, we will delve into the key components that make up the adaptive cruise control system. Understanding these components is crucial as they work together to ensure the system functions effectively. We will explore each component's role, how they interact, and their contribution to the overall functionality of ACC. Adaptive cruise control systems rely on advanced sensors to monitor and respond to the vehicle's surroundings. Let's explore the three primary types of sensors used in these systems. The most commonly used sensor in ACC systems due to their reliability and various weather conditions. Laser sensors are used in some ACC systems but are less effective in adverse weather conditions compared to the radar sensors. LiDAR emits laser pulses and measures the time it takes for each pulse to return after hitting an object, providing a high-resolution mapping. Among the various sensors used in adaptive cruise control system, radar sensors are preferred because they work effectively in adverse weather conditions like rain, fog, and snow, along with their affordability compared to LiDAR sensors. The radar sensor continually emits radar wave to detect the distance and relative speed of vehicle ahead. It collects data on how far the vehicle in front is and how fast it moves. Radar sensors are usually located in the front grille or bumper of the car. This positioning allows the sensor to have a clear view of the road ahead, enabling it to effectively monitor the distance and speed of the vehicle. The controller is the brain of the adaptive cruise control system, processing data from sensors and making critical decisions to ensure safe and smooth driving. It processes the data received from the radar sensor. It uses complex algorithms to analyze the distance and speed data, determining the necessary adjustment to the vehicle's throttle and braking systems. It sends command to the actuator to perform these adjustments in real time. It typically integrated into the vehicle electronic control unit. Its central location allows it to effectively communicate with various components of the ACC system and the vehicle overall control architecture. The actuator is the muscle of the adaptive cruise control, performing the commands from the controller to adjust the vehicle speed and maintain a safe following distance. It receives command from the controller and adjusts the vehicle throttle and braking system accordingly. This ensures that the car accelerates or decelerates smoothly to maintain the desired speed and safe following distance from the vehicle ahead. Actuators are typically located within the engine components, integrated within the throttle body and braking system. Their strategic placement allows for quick and precise adjustment to the vehicle's speed and braking, enhancing the overall effectiveness of ACC system. The display interface is the communication hub between the adaptive cruise control system and the driver, providing real-time information and ensuring driver awareness. The display provides real-time feedback to the driver about the ACC system status. This includes the current speed setting, a distance to the vehicle ahead, and any necessary alerts or warnings. It keeps the driver informed and engaged with the system, enhancing safety and control. The display is usually located on the dashboard or integrated into the digital instrument cluster. Its positioning ensures that the driver can easily view and interact with the information while maintaining focus on the road. Let's see the display interface in action. Notice how it seamlessly integrates with the dashboard, offering clear, real-time driving information right in front of the driver.
Hello, I am Ammar and today we will be walking through the flowcharts of an adaptive cruise control systems. These flowcharts outline the operational steps involved the ACC systems, from activation to speed adjustment. Let's begin with the first step. The process starts with the switching on the ACC systems. This can be done by the driver through the controls interface within the vehicles. Next, the driver sets the desired following distance and speed limit. These settings determine how closely the vehicles will follow the car ahead and maximum speeds it will travel. Once the distance and speed limit are set, the system checks the current speed is less than or equal 80 km per hour, for example. If the speed is greater than 80, the systems will adjust the speed to match the set speed. The next steps involve object detection. The ACC systems consistently maintaining the road ahead from any object, primary, others, vehicles. If no object is detected, the system is continuously to maintain the speed and surrounding. If any object is detected, the radar sensor is activated. These sensors play a critical role in measuring the distance to the vehicles ahead and its relative speed. It ensures accurate and real-time data is provided to the system. With the radar sensor active, the systems then measure the distance to the front car. This measurement is crucial for determining if any adjustment to the virtual speeds are necessary. The system compares the actual distance to the preset distance. Now, the system compares the actual distance measured by the radar sensors to the distance set by the driver. If the actual distance is greater than or equal to the set distance, the system maintains the current speed. However, if the actual distance is less than the set distance, further actions are required. When the actual distance is less than the set distance, the system activates the electronic brake. The steps is crucial for reducing the virtual speeds to maintaining a safe following distance. Simultaneously, the system reduces the acceleration of the car. By doing this, the ACC system ensures that the vehicle slows down gradually to match the speeds of the vehicle ahead, maintaining the present safe distance. Overall, these flowcharts provide a clear step-by-step process of how an adaptive cruise control system operates, from activate and setting preference to maintaining and adjusting speed. Each step is designed to ensure safety and convenience for the driver. Moving to the block diagram of adapt cruise control systems. This diagram illustrates the main component of their interact with the ACC systems. Let's go through each block step by step. We start with the driver setting the gap of the ACC. This involves selecting the desired following distance between their vehicle and the vehicle ahead. These settings is crucial to determine how closely the ACC systems will follow the vehicles in front. The next block in the vehicle system is the throttle control, brake control, and the ECU. The ECU is the brain of the vehicle control system, responsible for processing inputs and controlling the throttle and brake based on the ACC settings. It ensures that the vehicle speeds and braking are adjusting to maintain a set gap. Moving to the sensor systems, we have a radar sensors, camera sensors, and their detections capabilities. These sensors are essential monitoring the road ahead. The radar sensors measures the distance and relative speeds of the vehicle ahead, while the camera sensors provide visual data to assist the detecting objects and landmarkings. Next is the control system block, which is manage the ACC speeds and distance. These systems use data from the radar and camera sensors to calculate the actual speeds and the distance of the vehicles ahead. It compares the data to sets gap and determine the necessary adjustment to maintaining safe following distance. We also have the speed sensor, which continuously maintaining the vehicle speeds. These sensors provide real-time speed data to the control system, allowing it to make accurate adjustment to the throttle and brake.
Hello everybody, we're going to continue with the potential problem in ACC. We have first system delays, one of the critical challenges in adaptive cruise control system in system delays. These delays can occur due high latency in processing sensor data and executing control commands. Such delays are detrimental as they can lead to unsafe conditions where the vehicle may not respond promptly to changing road conditions. Therefore, real-time response is crucial for the effectiveness and safety of the ACC systems. Moving on to limit field of view. Another significant issue with adaptive cruise control system in the limited field view of radar sensors. These sensors typically have a restricted detective range, which means objects at extreme angle or coming from the side may not be detected, creating potential blind spots. This limitation can compromise the safety and effectiveness of the ACC system. Moving on to the next potential problem, which is system failures. System failures, whether hardware or software, pose a serious risk to adaptive cruise control systems. Such failures can lead to a complete loss of control, resulting in potentially catastrophic consequences and ensuring system reliability is paramount to the safe operation of ACC systems. After we talk about the problem, let's talk about solution. Here, the solution of system delays. Firstly, we can implement high performance processors that could process the system fast and avoid any delay. Second, we have used predictive algorithm to anticipate and correct adjustments. Third, we have optimized algorithm for fast processing. Moving on to solution to limit field of view. Firstly, integrate additional sensor with wide field of view that can scan the vehicle from each side. More important, we can employ 360-degree sensing system to eliminate blind spot and cover all the vehicle sides. Now moving on to the last slide, which is solution to system failures. Firstly, we can implement a special system for backup that can save the data and restore it anytime we want when the system fails. Secondly, we use fail system mechanism to maintain control once again when the system fails. Lastly, conduct regular maintenance and diagnostic.